Hi everybody, this week we're going to learn about redox chemistry. So I'm going to share a PowerPoint file with you. This is also posted on our Blackboard page for the class, and so you can follow along with those, or you can read the slides here. So we're going to start by reviewing some basics. So when we're considering redox chemistry, we need to look at the oxidation numbers. So one question we might ask is, are these two equations examples of redox reactions? In order to answer the question, we need to identify the oxidation number of each species. So let's go over the rules. So these are the rules for identifying oxidation numbers. The first rule is that in free elements, the oxidation number is 0. And examples of free elements include helium and hydrogen attached only to hydrogen, or any element that's attached only to atoms of the same kind. In monatomic ions, the oxidation number equals the charge. A monatomic ion is composed of an atom that has a charge, like sodium ion, calcium ion, or iron ion as examples here. Oxygen has the rule that the oxidation number is usually -2, and its exception is in peroxides, so things like H2O2, where the oxidation number is -1. The rule for hydrogen is that the oxidation number is usually +1. The exception for hydrogen is in binary metal compounds, such as sodium hydride, where you have hydrogen attached only to metal atoms. And in binary metal compounds, the oxidation number is -1. In fluorine, the oxidation number is -1. In chlorine, bromine, and iodine, the oxidation number is usually -1, but not always, so sometimes we have to figure it out. The next rule is a little bit of a catch-all, but allows us to figure out oxidation numbers if there isn't a rule. So the sum of the oxidation numbers is equal to the charge on the molecule or the ion. The rule is that if there isn't a rule, so this isn't exactly a rule, but if there isn't another rule for an element, but that element commonly makes a single type of ion, so like sodium ion is always +1, we can use that common charge as the oxidation number. So let's go back to our question here, and let's consider whether these two equations represent redox reactions. In order to do that, we need to look at the oxidation numbers. So magnesium in the first equation is a free element. It's all by itself, it doesn't have a charge, so its oxidation number is 0. And in oxygen here, it's only attached to another oxygen, so the oxidation number is also 0. On the other side of the equation, however, we have magnesium oxide. The oxidation number in magnesium in magnesium oxide is +2, and for oxygen now that it's attached to something other than oxygen, it's -2. If we look at any one element now, look at magnesium, it goes from 0 to +2. And let me get the laser pointer here. Right? So it goes from 0 on this side to +2 on the product side. And oxygen goes from 0 to -2. So now let's look at the next equation, right? Hydrogen in H2 is attached only to other hydrogens, so it's a free element. Its oxidation number is 0. Chlorine is the same in this case. And then on our product side, we have hydrogen chloride gas. And so now our hydrogen has a +1 oxidation number, and that means that our chloride is -1. I'm sorry, the air conditioner clicked on. That's what all the blowing was. All right, so in both of these cases, the oxidation numbers of our elements change. So for magnesium from 0 to +2, for hydrogen from 0 to +1, for oxygen from 0 to -2, and from chlorine from 0 to -1. So each of these represents a redox reaction. All right, many atoms don't have a specific rule for determining oxidation numbers. So then we can use this rule. The sum of the oxidation numbers is equal to the charge on the molecule or ion. Let's start by looking at phosphoric acid. Is there a rule for hydrogen? Yes. For hydrogen in a compound, the oxidation number is +1. Is there a rule for phosphorus? No, there's no specific rule for phosphorus. And then is there a rule for oxygen? Yes. For oxygen in a compound, other than a peroxide, the oxidation number is -2. To find the oxidation number for phosphorus in this compound, we set up an equation. Since the molecule is neutral, meaning there's no charge, the sum of the oxidation numbers will equal 0. Then we fill in the equation with the oxidation numbers we know. For hydrogen, we have 3 hydrogens. So we have 3 times the oxidation number we know, which is +1. We don't know what phosphorus is. And then we have oxygen, where we have 4 oxygens. Now we solve the equation to find the oxidation number of phosphorus. And so if we simplify, we find this. And then solving for phosphorus, we find that phosphorus has an oxidation number of +5. So here are some examples that you should work on your own. So you can either pause the video or you can look these up in the PowerPoint slides that are posted. So before we move on, let's just run through a few definitions, right? Something is oxidized if the oxidation number increases. Something is reduced if the oxidation number decreases. You may have seen these and defined them in terms of electron transfer before, but I think they make more sense looking at the oxidation numbers. An oxidizing agent causes the oxidation of another species. In other words, it is reduced. A reducing agent causes the reduction of another species. In other words, it is oxidized. And the redox couple is made up of the oxidized and reduced species, not in a half reaction as it says here, but in the overall redox reaction. One skill that we need to have is the ability to identify the species that is reduced and the species that is oxidized. Remember that they always come in pairs. Something must be reduced if something else is oxidized. So let's look at this equation as an example. Sulfur dioxide reacts with oxygen gas to form sulfur trioxide. In order to balance the equation, we need to add the coefficient 2 to both sulfur dioxide and sulfur trioxide. So now we want to answer the question, which species is oxidized and which is reduced? So let's look at the oxidation numbers. Oxygen is -2, and that means that, the sulfur in SO2 must be +4. Oxygen in O2 is a free element, and so the oxidation number is 0. On the product side, oxygen is -2 in a compound, and that makes sulfur +6. So the oxidation number for sulfur, there we go. Sorry, I knew I had the oxidation number somewhere. The oxidation number for sulfur increases from +4 on the reactant side to +6 on the product side. So sulfur is oxidized in this case. The oxidation number of oxygen goes either from -2 to -2 or from 0 to -2. So some of the oxygens are reduced in this particular equation. So let's practice balancing our half reaction or balancing our equations using the half reaction method. So let's look at this example. We're using the dissolution of copper in a silver nitrate solution here. So we have silver ion, and we have copper producing silver solid and copper ion. So first we need to write the half reactions. Okay. And for silver, we go from silver +1 to silver metal from the two sides of the equation. And if we have silver +1 becoming silver metal, that means that it gains 1 electron. Right? One way you can think about these is the charge on each side add up to the charge on the other side. So it's silver 0 here, so we have silver plus, so we need 1 negative over here. Okay. So this is the reduction. For copper, we go from copper solid to copper 2+, and that means the copper gave up 2 electrons. And that is the oxidation since it went from 0 to +2, so since it increased. To balance the equation, we need to have the same number of electrons for each half reaction. So we need to multiply the silver equation by 2 to have 2 electrons. So by multiplying by 2, we'll have 2 silver plus 2 electrons gives us 2 silver atoms. And at that point, we can add the equations to give us our balanced equation. And so we have 2 silver ions reacting with 1 copper solid to produce 2 silver atoms and 1 copper ion. Remember that your final equation should not include any electrons. Here's another example. So we have the reaction of tin ion with iodine to produce iodide and a different tin ion. So first we write the half reactions. So for tin, we go from tin 2+ to tin 4+, which means that each tin ion had to give up 2 electrons. This is the oxidation. For iodine, we go from I0, because this is a free element, to I- or iodide ion. Each iodine then gains 1 electron, and since there are 2 of them, we need 2 electrons here. So we have 2 I-. We need to make sure that we have the same number of electrons, and we do. We have 2 electrons in each, so we can add them together. So we have tin 2+ plus iodine I2 gives us 2 I- or iodide ions plus tin 4+. Right? So one question we could ask is, what is the redox couple in this case? And remember that the redox couple is made up of the 2 species in the balanced equation. So we have tin 2+ and I2, or iodine, as our redox couple. So sometimes we're working in an acid or a base solution. And so then we have to follow a little bit different rules. We can't just use the half reaction method. So the first step is to write the unbalanced half reactions, and we'll do an example in just a minute. I want to give you the rules first. Then we're balance the elements other than hydrogen. Okay, so that means, if you have copper or iodine or something like that. Then we're going to balance the oxygen atoms by adding water to the side other than wherever there's an unbalanced oxygen. Then if we're working in acidic solution, we'll balance the hydrogen atoms by adding H+. If the solution is basic, then we'll also add an equal number of hydroxide ions. In the next step, we balance the charge by adding electrons. In the next step, we'll make sure we have the same number of electrons in each half reaction, and then we'll add the half reactions. So let's look at an example. So let's practice by balancing the oxidation of iron 2+ by permanganate. if we have iron 2 plus oxidized in the reaction, we have iron 3 plus as a product. Permanganate ion, oh, and this shown in this first half reaction here, right? So iron 2 plus producing iron 3 plus, and that means it gave up 1 electron. Permanganate ion is MnO4 with a negative charge, and it is reduced to form manganese 2 plus. You can look these up in a table. So we're going from manganese plus 7 in permanganate to manganese plus 2. So now we're going to start following those rules, right? So we have oxygen atoms over here, and we don't have any oxygen on the product side. So what we're going to do is we're going to add water molecules to balance those oxygens. So 4 oxygens here, I need 4 water molecules on the product side. But now I have a different problem. Now I have 8 hydrogens over here, right? I have 4 waters, they each have 2 hydrogens. So I'm going to add hydrogens as H plus on the reactant side. So 8 H plus. We're working in acidic solution here, remember? And then to account for the change in the oxidation number, or I can think of this as balancing the charge, then I'm going to add electrons. I went from manganese plus 7 to manganese plus 2, so I need to add 5 electrons. So my half reaction here has permanganate ion plus 8 hydrogen ions plus 5 electrons produces manganese 2 plus and 4 water molecules. In the permanganate equation, I have 5 electrons. In my iron equation, I only have 1 electron, so I need to multiply my iron equation by 5. And then I can add the equations, and I find my final balanced equation in acidic solution. I have permanganate ion plus 8 hydrogen ions plus 5 iron 2 plus produces manganese 2 plus 4 water molecules plus 5 iron 3 plus. All right, so let's examine the reaction of zinc and copper in a galvanic cell. As shown in the image, a strip of zinc is immersed in a zinc ion solution. A strip of copper is immersed in a solution of copper ion. And the two are connected both via a voltmeter, so we can read the potential difference or the voltage, and by a salt bridge that allows passage of ions from one side to the other. Okay. That's essential for balancing the charge. The reduction potentials for the two reactions are shown here on the slide. Okay. And we can look those up in a table of reduction potentials. One question we might ask is, how can we predict the direction of electron flow? Well, we can look at the half reactions. In this case, copper is reduced to form copper metal on one side, right, on our cathode. And on the other side, zinc metal is is oxidized to form zinc ion. The electrons are transferred from the zinc to the copper, and the reaction will be spontaneous in the direction where that results in a positive potential or E naught value. The reaction is thermodynamically favorable in the sense that K is greater than 1 if the standard reduction potential is greater than 0. And the standard reduction potential is this E value. The standard reduction potential is the difference of the standard potential corresponding to the half reactions into which the overall reaction may be divided, right? So our half reactions here are these two. Remember, they're always written in the tables that we look at as reductions. So in order to calculate our cell potential, we usually flip one because we have an oxidation and a reduction occurring, right? In this case, we have zinc being oxidized and copper being reduced. And then to find the overall potential, we add those values, right? Just like when we're working with other parameters, if we reverse the direction of the equation, we change the sign on the potential. We can also look at the Gibbs free energy equations, right? So delta G equals negative RT natural log of K. And we also have delta G equals negative N. N is the number of electrons transferred times Faraday's constant times the potential. And from those equations, you can see that the reaction would be spontaneous if the standard reduction potential is positive, as a negative delta G indicates a spontaneous process. All right, so we're going to finish up by looking at two kinds of diagrams. The first is a Latimer diagram. Okay, and you can read more about the Latimer diagrams in the chapter, but I want to give you a little introduction to them here. The Latimer diagram is also called a reduction potential diagram, and in a Latimer diagram, the numerical value of the standard potential is written over a horizontal line or arrow connecting the species with the element in different oxidation states. So in other words, I have HClO2, and then on either side I have different species. And if you look, the oxidation numbers are shown below. So the oxidation number of chlorine here in HClO2 is +3. In ClO3 minus, it's +5. On the other side of HClO, where the oxidation number for chlorine is +1. The most highly oxidized form of the element is on the left, right? So over here. And it decreases as you move to the right. In this case, and often, the oxidation number is explicitly shown below the diagram. Sometimes you have to figure them out on your own. So let's look at this pair here where we have HClO and chlorine gas in a little bit more detail. So what does this diagram really mean? Well, this pair describes the reaction that's shown here, which we balanced using those exact same steps for balancing in acid or in base, right? So we have 2 HClO plus 2 hydrogen ion plus 2 electrons gives us Cl2 and 2 water. Notice that this does include electrons because this is really a reduction equation, right? So it's representing this reduction. The standard potential for this particular reaction, so conversion here or this equation here, is 1.67 volts. And remember, by convention, we write the sign for the reduction potential, whether it's positive or negative. So we would always put the plus in front. All right, 2 specific types of reaction that we need to be familiar with are disproportionation, which is a type of redox reaction where one species is simultaneously reduced and oxidized. So here's an example, and mercury is both reduced and oxidized in this equation, right? So in this case, mercury in Hg2Cl2 has a +1 oxidation number, where chloride is -1. Mercury by itself is a free element, so its oxidation number is 0. And mercury in mercury chloride has a +2 oxidation number. So this is an example of a disproportionation where a single element is simultaneously reduced and oxidized. On the sort of flip side, we have comproportionation, and I'll leave it to you to determine all the oxidation numbers here because this one's good practice. But a comproportionation is a reaction in which two compounds containing the same element with different oxidation states. So we have IO3 minus and we have iodide ion forming the same product, which has the same oxidation state. So both of these ions are being converted to iodine I2, which is a free element with an oxidation number of 0. So that's a comproportionation. Okay, so in Latimer diagram, a species has a tendency to disproportionate into its two neighbors. So we're looking at hydrogen peroxide here. If the potential on the right of the species is higher than that on the left. Okay. So the potential on the right here is higher, so 0.7 on the left, and I have 1.76 on the right. And so that will mean that hydrogen peroxide will tend to disproportionate. In other words, it will form these two neighbors. Okay. And because the potential on the right is higher, that means that hydrogen peroxide is a stronger oxidant than oxygen. All right, so lastly, we're going to look at Frost diagrams, which are a little bit different, a little bit more modern than Latimer diagrams are. And a Frost diagram takes a lot of the information from a Latimer diagram and combines it into a different visual form. Shown on this diagram are two different cases. The red line is a pH of 0 or the acid case. And the blue line is a pH of 14 or the basic case. And then these are, if we look at any one, we have all the different species with different oxidation numbers. So I have nitrogen 0, N2O where nitrogen has a +1, NO where nitrogen has a +2, and so on out here. Okay. The different species are connected by a line where the slope represents the potential difference. And we can tell whether species will tend to disproportionate or comproportionate depending on the particular arrangement of the different species on the line. So there's a lot of information you can pull from a Frost diagram, but we're just going to look at these couple here. So if we want to look for cases where we are going to have species that disproportionate,